Hey everyone, and welcome. Today we're going to dive into one of my absolute favorite ideas in all of mathematics, completely rethinking what the derivative is. We're going to be drawing from a real classic here, Marsden and Hoffman's Elementary Classical Analysis, specifically Chapter 6. It's some seriously cool stuff, so let's just get right into it.
All right, so let's kick things off with a question that really gets to the heart of why we need to do this. Yeah, back in basic calculus, we're all about the slope of a line on a curve, right? It's just one number that tells you how steep things are. But what happens when you're talking about a surface? Think about a rolling hill. There's no single slope, is there? If you take a step forward, it might be really steep, but take a step to the side, and it might be almost flat. How in the world do you capture all of that information at once?
Well, to answer that, we actually have to take a step back. We have to revisit the derivative itself and realize it's so much more than that little limit formula we all memorized.
And this, right here, this is the real secret. The most powerful way to think about a derivative isn't as a formula, but as an idea. It's the idea that if you take any nice, smooth curve and you just keep zooming in and zooming in and zooming in, what does it start to look like? A straight line. That straight line, the tangent line, is the best possible linear approximation of that curve, right at that spot. That's the derivative in its purest form.
So you see, the shift is moving from just a calculation to a core concept. The derivative isn't just a number. It's the best local linear approximation we can make. And that word approximation, well, that's our key to unlocking everything else.
Okay, so if the derivative is the best linear approximation, we can use that idea to level up. We just have to figure out what a linear approximation looks like in more than one dimension.
And this is where it gets really fun. Imagine you've got a function that takes a point on a flat sheet of paper and maps it to a point on a globe. How do you talk about the slope there? It's not just stretching things. The function might be twisting and rotating and shearing the paper all at the same time. A single number just isn't going to cut it. It can't possibly capture all that action.
So, what is it? What's the higher dimensional version of a tangent line? Well, the answer is so elegant, it's one of those things that just makes you smile. It takes all that complexity and wraps it up in one neat little package.
Okay, I know. That looks terrifying. That's the super formal definition straight from the textbook. But don't panic. Let's just talk about what it's really saying. All this equation means is that the change in our function can be approximated really well by some kind of linear map, which we're calling df of x. The rest of it is just a very precise way of saying that the error in our approximation disappears super fast as we get closer to our point.
So that's it. That's the big idea. In one dimension, the best linear thingy is a line, and we describe it with a slope. In higher dimensions, the best linear thingy is a linear map, which is just a transformation that does simple stuff like stretching and rotating. And guess what? The derivative is that linear map.
But you know, linear map still sounds a bit abstract, doesn't it? How do we actually write this thing down and work with it? Well, the beautiful thing is you already know the tool we need. In fact, you've probably been working with it for ages.
And here it is, the Jacobian matrix. It's our new derivative. All we do is we take every possible partial derivative, how each output component changes with each input component, and we arrange them all in a nice grid. This matrix, this simple grid of numbers, holds all the information about how our function is stretching, squishing, and twisting things at that one specific point. It's brilliant.
Now, the moment you accept that the derivative is a matrix, something incredible happens. All of a sudden, rules from calculus that used to seem kind of complicated and arbitrary, they just click into place and become super intuitive.
Think about the chain rule. Remember how messy that could get with functions inside of functions? Well, now it's just matrix multiplication. That's it. The derivative of a composite function is just the product of their derivative matrices. And it makes perfect sense, right? Applying one function after another is just like applying one linear transformation after another. This isn't just a neat trick. It's literally the engine behind things like backpropagation and artificial intelligence.
So this new matrix derivative doesn't just make old rules simpler. It also lets us solve all the classic problems in this bigger, more exciting world. Like, how do we find the very top of that hill or the bottom of that valley?
And the best part is, the logic is exactly the same as what you learned on day one. For a simple curve, where do you find a peak? You find it where the tangent line is flat, where the derivative is 0. Well, for a surface, you find a peak where the tangent plane is flat, which means our new derivative, the Jacobian matrix, has to be the 0 matrix. The fundamental idea is exactly the same.
So by just reframing the derivative as the best linear approximation, we've unlocked this whole universe of higher dimensional calculus.
But it does leave us with one last really juicy question. At a peak or a valley, the tangent plane is flat. Our linear approximation is 0. It basically tells us nothing about the shape. So how do we know if we're at a peak, a valley, or some weird saddle point? For that, we have to look even closer. And that, well, that's where the next part of this incredible story really begins.